Swayam Prabha. Digital India. Educated India.
Yeah? No more answers. Okay. Now, first look at this. So, AI is the event that the ith letter is in the ith envelope. Now, if I take union of AIs, what does it mean? That I am covering all permutations for which there is at least one letter going into its correct envelope. So, this union AI covers everything which is not a complete mess. Agreed? Right. Now, you know principle of inclusion and exclusion. Apply it. This is the sum of P of AIs minus sum of P of AI edges, so on and so forth. Okay. What is each one of the first terms? P of AI. What is the probability that the ith letter goes to the correct envelope? There are n choices, out of which one is correct, 1 by n, and there are how many terms in this sum? N. So, this is n into 1 by n. What about the next term? Two goes into its correct position, right. So, the first one goes, that probability is 1 by n. So, NC2 will come later because that is the number of terms. So, 1 by n into 1 by n minus 1, right. So, that is n choose 2 1 by n into 1 by n minus 1 plus dot 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 dot. So, finish it now. So, the next term would be n choose 3 into 1 by n into 1 by n minus 1 into 1 by n minus 2, so on and so forth till the last term. So, here you have 1 by factorial n and the index would be minus 1 to the power of. So, if you do this correctly and if you cancel out things properly, this looks like this, right. So, if you do this, if you work out this algebra, this would come to this. So, this was the probability of all kind of this non-messy things. So, what should be the final probability? So, this should be, I mean, I should not say it is exactly, but it is approximately. Mind you, we solved this problem without doing any counting almost, right. So, go back, when you go back to your homes, do this problem again, It takes a little while for this result to sink in. This is telling you that asymptotically, the number of letters really do not matter. As n grows large, this probability is approaching e to the power of minus 1, 1 by e. This is independent of n, asymptotically. Fine. So, that was an example of inclusion and exclusion. Quickly do union bound. This is a result which we will keep using again and again, again and again. Now, see, when you, for example, when I did this example on derangements, it was easy because I could handle this AIs, AIJs, AIJ, AIKs, all these k-way terms. But when you look into real life examples and you know do a probabilistic modeling of it, there would be times when getting these intersections and having an estimate on their probabilities would not be that easy. At that moment, union bound is one that allows you to put a bound on this probability, that no matter how these events intersect, no matter how they are related, this holds. So, the union bound is like what I said at the beginning when I was discussing the axioms, it is right. So, we will see nice examples of this in the tutorial as well as in a few of the lectures. So, what is this saying? That see, I did not have any restrictions on these events. So, you take unions, and again it is like for our case, as I said, this holds for countable sets. Fine. Think of writing a proof for this. Okay. So, take an exercise. Prove it. We will do it in the tutorial as well. Again, you have to start from axioms and build on. So, you have to write union of AIs again in terms of some disjoint sets. The challenge of this proof is, how do you write union of AI in terms of some disjoint sets? Okay. I'd rush a little bit, I would not go into this proof, neither would I go into an exercise on union bounds, maybe we will do it in the tutorial. Okay. Now, let us quickly jump over to conditional probabilities. So, what is a conditional probability?
Remove event K is the probability of an event given that particular event is occurring.
And this you know to be by okay. Now, what this is telling you is, earlier you had the sample space omega with you. Whatever probability that you are doing, so defining those measures, defining these looking at those axioms was on the sample space omega, right. Now, this is asking you to focus your attention only on the set P. Now, see, the moment this entire theory that I had built till now was on the sample space omega. Now, you have come down to B. What is the guarantee that this quantity that I have written, this probability A given B, is also a probability measure? This might not be a probability measure. I have to first verify that this quantity on the left satisfies all those three axioms. If it does, then I can continue doing whatever I was doing earlier with sets on probabilities. See, this A given B is really not a set, right? You cannot say it in terms of a set. Earlier you were defining probabilities on sets. Now this is telling you A given B, and then you have this nice definition, fine. Who said this is a probability? And if this does not satisfy those axioms, then you cannot do anything further with this, right. So, take this as an exercise. See, what actually happens here is you replace A with B. On the right, what you get? 1, right? It is B intersection B. that is B. So, probability of B by B, and there is a small caveat in here that I require probability of B to be strictly greater than 0. So, B has some probability mass in it. So, this is telling you probability B given B is equals to 1. In your earlier axiom, what was it that was having the probability equals to 1? Sample space, right, the entire sample space. So, this is telling you that your new sample space is B. I will not look here and there, I will just focus on B. So, that is conditional probability. Now, a nice follow up of this is now there is a nice extension of this which we will do and you can prove. It tells you that this is known as the chain rule. So, I am looking at the intersection of n events. I can write it as multiplication of so an intersection, an n-way intersection, I can handle it using conditional probabilities. How? I take the first term, multiply it with A2 conditioned on the first term into A3 conditioned on the intersection of the two events, so on and so forth, right. You can see an easy proof of this. What you do is essentially, again this holds when all of these probabilities have non-zero mass, right, because always remember in conditional probability the conditioning event should have a probability greater than 0. So, look at each one of these terms. So, the second term would be probability of A1 intersection A2 by probability of A1. So, A1 should cancel out. So, if you write this out, what will happen is this cross terms would kind of cancel out and what would remain is the last term which is the intersection of everything. So, this is a thing that I will use when we talk of min cut in graphs in tomorrow's last lecture, right. So, we will see a nice application of this later on. So, I say two events A and B are independent if this happens, that no matter how you condition A by B, B is not going to influence the probability of A, right. Now, if you open up the left side, it is probability of A intersection B by probability B. So, consequence of this is, now note that there is a symmetricity of this expression. So, probability of B given A should be probability of B, right. From there also you can come to this relation, that probability of A intersection B is equals to probability of A into probability of B. So, these are symmetric, right. If A is independent of B, B is independent of A. Okay. Now, quick exercise. What do you think? Yes, no, maybe, maybe not. Right. So, think over this exercise. The answer is they can never be independent, right. But think of a proof of this. Okay. Now, we handled independence of two events. Obviously, we want to extend this, right, getting to independence of a collection of events. Okay, maybe there. The answer is no. Fine. Follow this notation a bit carefully. So, this is a very strong requirement. I am saying this should hold for all possible subsets of the sets 1 to AI to A1 to An. Then I say they are independence. So, this is a very strong notion of independence, right. Now, I will give you a small example where I will show, take a few n to be small and show to you that pairwise independence means that A1 A2 being independent, A2 A3 independent, A1 A3 independent, so on and so forth, does not necessarily imply that the events A1 A2 A3 are all independent, right. So, again Udalak put this in an exercise, show that pairwise independence does not say necessarily imply independence as defined earlier. So, try to think an example where pairwise independence, there may be situations where pairwise independence imply mutual independence, but this will not generally hold true. You can surely come up with examples where pairwise independence will not imply mutual independence, and this result, this degree or level of independence would be very important when we discuss hashing and the space used when you use hashing. Maybe you can do another exercise after I discussed conditional probability. Look at derangement through the lens of conditional probability. Try to prove the same result that we proved in derangement through conditional probability. Okay. You have enough exercises to work in home, and myself and Uddala could put this in a tutorial sheet and possibly give to Professor Somasundaram, so that by tonight things are uploaded, right. Fine. Maybe I will quickly move into random variables and finish the day, and then again take up tomorrow. Well, any questions till now before I get into random variables? So, what we have done is we have seen probability axioms, we have seen union bound, we have seen conditional probability, we have known what is independence, we have known that pairwise independence does not necessarily imply mutual independence. So, you have to be very cautious in there when you talk in terms of the degree of independence. We will quickly now get into random variables, but before that any questions?
Mutual exclusive independence are two different things, or they are same term for the different?
No, that is what I said. Mutual independence means
Mutual exclusive and independent, these two terms have the same meaning, or they
mutual.
are exclusive
So, if two events are mutually exclusive,
and independent, then
and then that means they are disjoint, right? Right. Exclusive means there is no intersection, so they are disjoint. And then we have argued that I have given you an exercise which tells you that mutually disjoint events cannot be independent events. And this definition is the definition of mutual independence. Now, see, this is a very strong definition, because I am asking you so that this holds for all possible subsets of 1 to n. If this holds, then I say that these events are mutually independent. Otherwise, they can be pairwise independent, they can be 3-wise independent, they can be 4-wise independence. But if you want the full scale of independence, then this is the definition, and it is a, mind you, this is a very strong definition. Okay, now quickly getting into random variables. So, a random variable x on a sample space omega is a function, or I might even say it is a real valued function, that is okay. So, when you think random variables, you think functions. It is a function from a sample space to a set of reals. Say for example, you are forming random variables from your favorite dice throwing experiment, right. Your sample space consists of 1 throw, 1 to 6, right, and for each one of them you assign a real value, and that can be a probability. Fine. Now, what do I mean by this statement?
at time particular t, the function.
Where do you find time?
All
There is no time in here.
okay. I want to say that at the real value for x is equal to a, what will
See, the point is, hold on. Mind you, probability is over sets. So, this x equals to a should give to you the meaning of a set. Now, think of this in your favorite dice throwing experiment. If I say that the sum of 2 dice throws, where your sample space has 36 points, is say 9. So, I write x equals to 9. What does that mean? That 3 6 is one that gets to 9, 4 5 is another that gets to 9, 5 4 is another that gets to 9, 6 3 is another that gets to 9, right. So, it is a collection of things in the sample space that takes the value A, right. So, this notation is now making sense to you. So, you can think it in terms of probability of some S such that this S belongs to the sample space and your xs is equals to A. Now, before getting into independence or other things, let me define the expectation of a random variable. This is kind of the average value that this random variable takes. So, you have corresponding to this random variable, it takes a few values. Okay. Now, mind you, again as we are dealing with the discrete world, my random variable, the random variables that we would consider are also discrete random variables. So, that means the values that they take come from a discrete world, right. Okay. So, you will have their corresponding probabilities, and expectation is nothing but these things taken product together and then you sum them, right. So, simply put, expectation is nothing but summation x into px of our favorite random variable will be a 1 0 random variable. This is one thing we will keep using again and again, and say it comes with a probability p, and so then this comes with a probability of, these are known as, in computer science we call them to be Poisson trials, where a trial has only two outcomes, like in your coin toss case, head and tail. One we label with 1, the other we label with 0. 1 comes with the probability of p and 0 comes with the probability of 1 minus p. So, then what is expectation of x? Which is, so p into 1 plus 0 into 1 minus p. So, expectation is p. So, what is p? P is nothing but, so the expectation of a 0 1 random variable is nothing but the probability of x taking the value 1. So, there is another result on expectations which helps us hugely, is known as linearity of expectations. So, for two random variables x and y, you can obviously make a generalization of this. So, maybe not today, but tomorrow I will define the notion of independence of random variables, but linearity of expectation does not care anything about these random variables. So, if you can sum up these random variables and take their expectations, it is equivalent to taking the sum of their individual expectations. This result even holds if n is countably infinite under certain conditions, but let us not get into that. For us n is a finite quantity, right. So, linearity of expectations holds for countably finite many random variables. Now, think of this exercise. Say you have n cards with their faces down, right. What you do is you are trying to guess these cards. One guess is without any memory, say you do not have any memory. So, what you do is you go to a card and predict that it is, and this cards has these numbers 1 to n written on them, arranged in any arbitrary fashion. So, you go to a card and predict that it is this number, right. Mind you, you have no memory, you overturn and see. So, if you have said correct or not. Go to the second card, again predict and see if it is correct or not. So, this experiment is clear. The question is, on the expectation, how many correct guesses would you make, right? This is one problem. So, this is memory less guessing. We can do a memory guessing, where you go to the first card, you open it, if it matches fine, you either way open it. So, it can be a match or a mismatch, but after overturning it, you know the number, now you remember it. Go to the second card. When you predict on the second card, you are obviously not going to say the first number because you have memory, again you see it, you remember this two, go to the third, keep doing. The question is, on the expectation, what is your number of correct guesses, fine. So, do this two exercises to see as an application of linearity of expectation. Now, here is another problem. You are, say you have gone to a shopping mall and they are selling, say, jeans of different brands, and you have a huge box consisting of jeans of all these n brands that is available, and the shopping mall tells you that if you buy jeans of all brands, you are going to get something for free. Now, the random experiment that you do is, you pick a jeans, right, uniformly at random from this box. It is of a brand, say Levi's, fine. So, you have got one brand and this was a sure shot thing, right, you have picked a new brand. Now, you pick another, this can be Levi's or something else. Now, you keep picking up jeans till you get the second new brand. You have got two brands, but you have bought maybe more than one. Now, again you pick up something new. Do this till you get the third new brand. You keep doing this till you get n new brands. So, how many pieces of jeans would you buy on the expectation? Any hunch? Make guesses. It has to be more than n, surely, right? That is for sure. And you understand that towards the end you have to buy more and more. Think about this. Okay, we stop here and again continue from the tomorrow's morning.